Look at this cute 5-room bungalow home. The Wellington, only $1,988. And it's got this great blueprint that shows the dimensions of the finished house. This is an awesome starting point for our history project in building scale models of historic architecture. But if we're going to scale this down from real-world sizes to something much smaller that we can 3D print, and if we want our 3D prints to fit together, build a small city, they need to be the same relative scale. Scale is how we go from large, real-world sizes into a smaller version that keeps the same proportions. To do this, we're going to have to do a little bit of math, and I've made a simplified blueprint with the dimensions I want to use. The first thing I notice is that these measurements are in feet and inches, indicated by the single quote and double quote marks after the numbers. The single quote references feet, the double quote inches. Some of this is pretty straightforward. I see that the main width is 24 feet wide, but other measurements are 9 feet 2 inches. We want to change this so it's one consistent unit of measurement. We're going to go from inches to feet, and then add that decimal value to the overall dimension. Since there are 12 inches in a foot, all I need to do is take the number of inches divided by 12. For something like 6 inches, that's easy. That's 1/2 of a foot. I don't even need a calculator for that. But 2 inches, that's a little trickier. 2 divided by 12, I use a calculator. I get the decimal 0.16 repeating. I'm going to round that here. Let's call it 0.17. That cleared up my inches in feet problem, but now I got to address how do I go from full size in feet to a small size in millimeter that I would design in my CAD software. I'll need to convert from feet to millimeters, but also reduce it in size at the scale I want to use. We'll be using N scale. That's a model train building scale, and it has a ratio of 1 to 160. 160 units on my model will equal 1 unit in the real world. To go about this, let's review some math background that helps us understand how we can manipulate numbers. 7 times 6 is 42, and 6 times 7 is 42. It doesn't matter what order I put these numbers in, the product is the same. This is called the commutative property of numbers, and it means I can rearrange numbers if I'm only multiplying them. 1 times 2 times 3 times 4 is the same as 2 times 4 times 1 times 3. Another useful math fact, any number divided by 1 is itself, so 7 over 1 is equal to 1. 4 is the same as 4 over 1, and 5 is the same as 5 over 1. Sometimes it's useful to express a number as a fraction by putting that number over 1. Another number property, any number divided by itself is equal to 1. 7 divided by 7 is 1, 4 divided by 4 is 1. This is also true for units. Feet divided by feet equals 1. Cans of soup divided by cans of soup also equals 1. When we do this, we say we cancel the units. Feet over feet no longer has a unit, it's just a ratio. For example, 1 meter in the real world divided by 160 meters in our n-scale world equals 1 over 160, because meters over meters is 1. For our project, we're going to want to go from feet to millimeters at n scale. The steps to do this will be going from feet to inches, from inches to millimeters, and then millimeters in the real world to millimeters at n scale. Let's look at the width of the house first. It was listed as 24 feet. I can convert it into inches by multiplying it by 12 inches in 1 foot. I put the 24 feet over 1 to create a fraction, and I can simply multiply the numerators and multiply the denominators. When I do this, the feet in the numerator will cancel with the feet in the denominator, and I'll only be left with inches. That is because I can use the commutative property to rearrange the fraction and show it as the same thing as 24 times 12 inches over 1 times 1 times the fraction feet over feet, which we know also equals 1. My result then is simply 24 times 12 inches, 288 inches. That gets us partway there. Let's complete the math to figure out how big I need to make this in the CAD model to create a scale version of this house. 24 feet over 1 times 12 inches in 1 foot times 25.4 millimeters in 1 inch times our scale ratio, 1 over 160. I can cancel feet and feet, inches and inches, and I'll be left with the number in millimeters at end scale. I multiply the numerators and divide by the denominators. The result is 45.72 millimeters. I'll round that to 46 millimeters when I build my model. Let's look at another side. This long side is 40 feet. I write 40 over 1 times 12 inches in 1 foot. Feet cancels, and I write 25.4 millimeters in 1 inch, and inches cancel, and I multiply that by 1 to 160. This side, 76.2 millimeters, I'll round to 76 millimeters in my finished model. Let's try it with this dimension that has a decimal in it. I write 9.17 feet over 1 times 12 inches in 1 foot. Feet cancels, and I write 25.4 millimeters in 1 inch, and inches cancel. I multiply by my ratio, 1 to 160, and I get 17.5 millimeters. I'll leave that number like it is. This process of writing fractions and canceling is called dimensional analysis, but you might notice I keep doing the same steps over and over again. I can simplify this a bit by just solving the feet to inches, millimeters to inch, and scale ratio, and I come up with a number that I'll call my scale multiplier, 1.905 millimeters for each foot at end scale. If I take that number and multiply it by any of my dimensions, for example, 5 feet times 1.905, I'll get an answer that represents this dimension in millimeters at end scale. I can simply use my calculator and this new scale factor I made to find the dimensions of the other sides that I need. And this number, 1.905, is very specific to this scale. And this number, 1.905 millimeters per foot at end scale, is very specific, but if you're one of our students and you're building at this scale, you can use this number too to calculate what size each dimension of your building should be. Thanks for watching. I hope this helps you complete the math portion of building scale historical buildings.